we are going to start limits, introduction to limits and continuity. So we are going to study about two things, and one will be continuity, and then after that I'm going to get into a little bit deeper thinking about the limit. So I want to talk about, there are two kinds of graphs. Of course there are a lot more graphs in reality, but there are two kinds. If I put as a CTS, that means continuous. So there are continuous function. Also there is a not continuous function. And another way that we say not continuous function is a discrete function. And those are the functions not continuous. And we are going to also find what is the limit of the infinity today. So continuous functions are example of y is equal to mx plus b as a linear equation. Also, you know that quadratic function as x squared, these are the all continuous function. So basically all the functions that you guys have learned are all continuous besides rational functions, which is at 0 you have a vertical asymptote. So what is a discrete function then? So discrete function is usually we use in computer. So those who are going to take a computer science major, they are going to study discrete mathematics because the computer only takes 0, 1 and there's no between. So those are kind of numbers we call as a discrete numbers or discrete mathematics. So in calculus, always our function has to be continuous, and then later on we are going to find rate of change. So we are going to always study continuous function, or we like to be continuous. So let's look at example 1. So I want you to actually pause the graph and then think about how many parts or where does this graph is not continuous. So if you want to just pause the graph and then do quickly. Okay, how many do you see? You can answer for me actually. How many do you see? I will cut this part. So for me, I see, I don't know if you can see the graph really clearly. Okay, I'm gonna cut this part. So if you're gonna see this graph, I see that 1, 2, and 3 parts is going to be disconnected. So what I see is when you follow tracing your graph, I see that there's an open circle. That means I have to lift my finger. So at x is -2 is disconnected. Another piece when you get here at x is 0, it is disconnected. And then from here, all of these ones, you can draw it at one drawing. And at 6, also you are going to have graph with disconnected. So where it's not continuous, it's going to be -2, 0, and 6 as x coordinate. Why we have to find that? Because if it's not continuous, we cannot find the rate of change. So we only get to find the rate of change where the graph is all continuous. So I want to actually talk about some of the meaning in here. I'm going to go straight forward and then explain to you what limit is with using the example here, and hopefully you can catch what limit means. So limit is actually meaning of the number where it's heading to. So it may be a little bit confusing, but just let's look at the example with me. So f of -2. If you look at the graph carefully, I want to see that what you see here. Do you guys see y value as 1? Then what is the limit of x approaches to -2? So there are different meanings here. This one is a function at -2. Function means 1 input, 1 output. So I have a -2 will give me 1. However, now limit means the number around that. I'm not talking about exactly -2. It can be -2 if it's continuous, but this case, what will be the number heading to if it's x is close to -1.999 or x is close to 2.0001 with negative. Those are the number I'm looking for. So if you look at the graph carefully, limit means in this case, when x was -2, I get 3. Why? Because do you see my values are here going to 3. So I'm not talking about the value at -2, I'm talking about the number around here. So where are they heading to? They're heading to value of -3. This kind of idea is actually very related to AI developers, because you have to keep training and then try to make limit goes around your goals. So this will be related to some of the idea of AI studies. Then after you look at, if you understand B, I want you to think about what C represents. It's hard to see here, but it says a 6 plus. So if you look at 6 as a plus means right side. 6 as a negative means 6 of a left side, like a 5.9. 6 with a plus means like 6.1. It can be 6.001. So this time my limit is going to be actually coming from this side. And then although this open circle, I'm talking about where number going close to answer 1. If you got the idea, then try to answer rest of them quickly. And then let's see if you can get the correct answer with me. So you can also pause it and try. So D, look carefully. For me, I got the answer 2.5. And then next one at 6, this is important meaning in here. I want you to look at carefully. So limit at right hand side, I got 1. Limit from the left hand side, I got 2.5. Then what is the limit at 6? This time we say do not exist. Because one come from different number, other side come from another number. That means it's not going to be continuous. That's kind of a meaning later we are going to put as an official definition. So if it doesn't have the same limit, then we say that at that point, limit do not exist. But does right side exist? Yes. Left side exists? Yes. But at that point, do not exist. Then what of the function of 6? Function at 6 will give me 2.5. And then last one. I want you to try last one. What do you think? When x goes to 0, so if you see this one will be also do not exist. Because when you look at left side, my limit goes to -1. Right side goes to about 4.5. 1, 2, 3.5. So at 0 do not exist. But when x goes from 0 plus, then yes, I do have a limit, which is a 3.5. If x comes from 0 minus, then I have a limit of -1. Okay. So if you understand this part, I actually wanna add another important definition here. So if you understand continuous, I wanna talk about if limit exists. We already talked about 2 examples. One of them in here, does a limit exist at 6? And answer is no. How about does a limit exist at 0? Does a limit exist at 0? Then that was also no. Then what does this tell you? If limits are not the same left side and right side, we officially say that that's not continuous by mathematics definition. So that's how we prove it. Like when you look at the graph, oh yeah, they are not connected. But I know that. How do we explain it in mathematics? Using limit definitions. Okay. So let's look at one class activities. So in here, if you look at my function is a 2x squared minus 3x plus 4. And what is the limit at 3? What should I do? First of all, check that. Is this function continuous? Yeah, it is continuous because I know that quadratic function is always continuous. Then, do I have a limit at 3? Yes, I'm gonna have a limit 3. I don't know where it's gonna be, but let's say there will be my y coordinate because it's continuous. In that case, how do we compute the limit of this value? Can I just plug in? Because my value will be continuous step that is the same as my limit. So if I plug in carefully, 2 times 3 squared is 9, minus 3 times 3 plus 4. So if you do calculation, 18 minus 9 plus 4 makes 13. So I can say that the limit goes to 13. And I want you to know why, because this function is continuous that I can plug in my number directly. Class, now let's start the appetizer part of the example 2. And some of them I'm gonna repeat so that you understand some of the pre-calc material and then calculus material here. So some of the functions you see 1.7, 8, and 9, I'm gonna keep repeating until you understand. So I'm going to give you 3 seconds. Try to graph y is equal to x plus 1. So starts at 1 and slope is 1. So we are going to have a linear function, looks like this way. Then I like to compare this function with next one. We actually saw this one the other day, 1.6 last questions. I briefly explained about 1 minute. So if I look at this one, looks like a rational function, I'm going to factor okay, I'm gonna cut this part. Okay. Now you see how I record. I'm going to factor, and as you see, this cancel out, then my equation turn out to be same. Does that mean do we have a same graph? Yes, actually we do have a same graph, so I'm going to draw x plus 1. However, what's the difference is in here? When you have a rational function, when your factors reduce each other, that means I cannot have value 1, so I'm going to have a whole at 1 here. So basically I get same graph, but when you see this is scary, factor it and then you get the linear equation, but one difference is their domain. So let's compare quickly. The domain for linear equation is going to be all real numbers. However, this one is all real numbers but 0, since you cannot have denominator 1. Then what will be the asymptote? The asymptote will be, we don't have asymptote because that's a linear equation. This one look like we will have asymptote, but actually we don't. Why we don't have an asymptote? Because after you divide, that's what you get as an equation. It doesn't look like any more rational function like that. Then now I want to talk about end behaviors as a limit. So I'm gonna start introducing limit here. So end behaviors we can describe as a limit here. So as x goes to infinity, where your function x plus 1 goes to, as you see, my graph is gonna be going to infinity as x gets bigger. Then how about x goes to negative infinity? Then my function is gonna go to negative infinity. What I just said is exactly definition of a limit. This is, we just write it as limit symbol, x goes to infinity of f of x. That's what I just said. And then it goes to infinity. Just look at how I write it here. That's one of the way writing limit. We like to write it fancy way in mathematics. So we're gonna write limit x goes to negative infinity of a function f of x, which goes to negative infinity. Then I want you to think about what is the limit at 1. How are we gonna write this one in our notation? Limit x at, when x goes to 1, what is my output? Can you guys compute that? And as you saw previous example, this is a continuous that at 1, I'm going to have value 2. You can directly plug in because my function is continuous. The next one, I want you to compute rest of them here again. So we talked about asymptote is not existing, but also we can talk about end behaviors. How are we gonna write it end behaviors here? Let's learn that limit notation. Limit as x goes to infinity. My function of f of x, well, let's call this one as h because this one I call as f. Then that's also same thing, goes to infinity. Which means as x goes to infinity, function f of x goes to infinity. That's the same thing. Let's do one more time. Now we can do negative side of the end behavior. So as negative infinity, x goes to negative infinity, my function, I keep saying as f, as negative infinity. Then what is the limit at 1? What is the limit at 1 in this case? What do you think? Do we have a limit at 1? Yes or no? It's weird, right? This one, yes, we have a, which is a 2. Young, why is that 2? Just look at from x as 1 negative side, left side, is it heading to 2? Is it closing to 2? And x coming from positive side of the 1, is my number getting closer to 2? I cannot say exactly 2, but getting close to 2. So we just talked about the definition of a limit exists at that point. Then, yes, limit exists, which is 2. However, do I have f of 1? Do I have f of 1? No, we are not going to have that value because domain says we cannot have 1 here. So just think about limit concept. I'm just looking around the number around that. So if it's 1, I'm looking for the number a little bit less than 1, a little bit bigger than 1, where those number going to. I forgot to mention about continuous here. So that's a big differences between these two functions. yes, first one is continuous. And is the second rational function continuous? No, this is not continuous. Where at 1 is not going to be continuous. So that's going to make huge differences in calculus. So let's make our definition. So what does continuous means? Your continuous means your limit has to be same as your function value. Your limit value has to be same as your function value. So look at here. Why do I not have a, this one we had a limit. However, is this continuous? No, it's not continuous because this one do not exist, but your limit exists at 2. So this one says limit is 2, but this one do not exist. Therefore, this function is not continuous. That's how we prove it. And then here I just briefly write it down my own definition of a limit. You can also look it up the textbook or Google it, but limit definition is really abstract. So I want you to think about it as just a number nearby or where is that number is heading to. That will be a good way of remembering what limits. Now we are going to have the main dish part. So I hope that you understand limits. I'm going to explain a little bit more about the limit in here. First, let's see if we can sketch the graph. So first one, second one, and third one, I will help you to graph. And then you will be seeing graph like this often. So earlier we studied about x minus 3 over x minus 3 kind of equations. If I have this one, what's going to be? This is going to be equal to 1, right? However, now I want you to look at this graph by plugging some points. So I know that my graph is going to be 1, but it's going to be everywhere. If I plug in the number 5, I want to plug in 5, then that's going to be absolute value of 5 over 3 and 5 minus 3, that's going to be 2 over 2 as 1. How about if I plug in negative 5? If I plug in negative 5, then it's going to be negative 5, negative 3, absolute value, and then negative 5 minus 3 will make 8 over negative 8. I get negative 1. So, as I see that sometimes I get 1, sometimes I get negative 1. What's it gonna be? Well, you have to see by plugging all the points. I want you to try to plug in points 4, 3, 2, 1, 0. Then if you plug in 4, you will get 1. If you plug in 3, what happened? It's gonna be, as you see, undefined since it's next to 0. When I plug in 2, that's going to be negative 1, negative 1, negative 1. So my graph will be 1 up to 3. And then negative 1 before 3. So remember, this graph is going to pop up often today. So that's how we're going to graph. Then I want to talk about if there's a limit exists. So I want to see if the limit exists at 3. Do we? When I look at this one, I can see that limit do not exist because my left hand side of the limit is negative 1. My right hand side of the limit is 1. That limit do not exist at 3. But does limit exist at 3 negative side? Yes, this case, I do have a limit exists as a negative 1. Right side, yes, limit exists as a 1. But at 3, does limit exist? No, because these two are not the same. Also, not continuous. Let's look at next one. Next one, we have seen this one last class too. So briefly pause and then you can graph and then check the answer with me for your graph. So I graph mine this way. We are going to have a x-intercept and asymptote, horizontal and the vertical lines. Then again, we want to find the limit exists. I'm going to write it down for you. So limit as x goes to infinity. Does 1 over x squared, do I have a limit? I want you to think about that. Do I have a limit? In this case, yes, I do have a limit, which is 0. As you see, my graph is following my x-axis, so limit exists, which is 0. Then I want to ask one more. When x closing to 0, does limit exist? I want you to think about it. Do we have a limit here? In this case, it goes to infinity. The limit goes to infinity. How? Because when you see it, my number whenever close to here, as you see, my graph is increasing really fast, so that number is gonna be look like a very big number. So there's a limit exists. But I want you to also think about here, you actually saw some definition. Do you recall as what does this mean? This is a definition of horizontal asymptote. How we find the horizontal asymptote. And then this one, also another way of finding vertical asymptote using limits. Vertical asymptote using limits. Also, you can think about this way. I have a function 1 over x squared. We are going to talk about a lot. X value becomes very, very small, like at 0.0001. What is that? This number is actually 1000, something like that. So you can actually see whatever the number denominator gets smaller, actually that means become very big number. And last one of the example 2, let's graph the sine function. Sine function is going to be line between 1 and 0. Just gonna draw it roughly this way. And then let's put this as a pi and 2 pi. So I have a sine function. As limit x goes to infinity, does the sine function have a limit? Yes or no? In this case, since you know this graph is going to be repeating up and down, the limit do not exist. Because we don't know if it's 1, we don't know if it's a 0, we don't know if it's a negative 1. So we cannot say that if a limit exists. Then how about if I say x at 0? Does the limit exist? In this case, yes, because it is a continuous function, I can plug in 0 here, sine 0 is 0. So limit exists. Then just be careful when limit do not exist. When limit do not exist, when it is split it like this, left side, right side are different. Also in this case, when we have a vertical asymptote and then when it goes infinity, as we write as infinity, which is I'm okay with you guys, but in mathematically we say this one also do not exist. Just going to infinity, you cannot say exact number what it is. And then other one is alternating cases, go up and down like a sine cosine function, then we will say limit do not exist. So you get to see 3 big examples of when the limit not existing. And remember that. So I put another in-class activities. I want you to pause the video and then try these 3 questions quickly and then compare the answer with me. They are very related to previous one, so good luck. Okay, so if you get to finish in-class activities, compare the graph with me and then let's see if you can find the limit. Try not to see my answers first because it will be easier if you see it. Just try to see how we can graph. As you see, this one we can reduce to 1, this one also reduce to 1 or negative 1, from 2 to bigger and 2 to smaller. And then last one, after you factor out, it turned out to be 2x minus 4 graph. So please do before you look at my answers. And let's look at limit at 3. So if you look at this one, limit at 3, since it's continuous, I can just plug in, which will be 1. But what will be the limit at 0? In this case, do we have a limit at 0? Yes or no? Answer, yes, we do have a limit, which is 1, because the left side, right side, they are coming towards to 1. So although we don't have a value at function, although it's not continuous, left side, right side is the same, so limit exists as 1. Then next one, it's a very similar question to the other one. If you plug in number, you will get the graph right away too. So if you are not understanding, just plug in numbers 5 through negative 3. Then let's compare what is the limit as x is at 2. At 2. Do you guys see that? Do I have a limit? This one do not exist because they are negative 1 and other one is 1. And the f4, do I have a limit? Yes, which is 1. Since it's a continuous at 4, I just plug in. Last one, then what is the limit at negative 2? When I look at this one, what is the limit at negative 2? Do we have limit? Yes, we do have a limit because when you see it, although it's not continuous, I see that this direction and the other direction both coming into the same number, which that number is going to be negative 2 times 2 minus 4, which is negative 8. So it's heading to negative 8, although I do not have f of a negative 2 value. Although I don't have them, I have a limit in here. So remember, what does a continuous mean? So I'm going to briefly summarize continuous and limit again. Continuous means you're comparing function to limit. Your function has no value and then limit has a negative 8. So in this case, we say that it's not continuous. And what does a limit mean? Limit means left side, right side. Are they going into the same number? Then yes, limit exists. Let's start the main dish part of the example 4. Let's look at the graph of next rational functions. It shows as a 1 over x squared plus 2. If it was 1 over x squared minus 2, that was a little bit easier to graph, right? Then this time I have a positive s here. So how are we going to graph this one? Last time I went through thoroughly, so I want you to also see that if you can compute all of those things. So first, if you remember how we graph this one using rational functions, domain, you see that it's all real numbers. And then it's going to be vertical asymptote. I see that vertical asymptote, we don't have it. Because nothing makes denominator 0, so we do not have vertical asymptote. We don't have much information. Horizontal asymptote. Do I have a horizontal asymptote? If you take a long division, 1 divided by x squared will give me 0. So my horizontal asymptote is going to be this. And then let's find the x-intercept, which is y is 0. If you plug in the 0 over 1, you get 0 is equal to 1. So you don't even have x-intercept. Do I have a y-intercept? This hopefully have a y-intercept. Yeah, at least we have a y-intercept. Plug in 0 gives me 1 over 2. So that's all I have. So how are we going to graph that one? I want you to think about related to reciprocal function. What is the reciprocal of this function, which is x squared plus 2? Do I know the graph? Yes, my graph is going to be at 2 and then parabola. Then as you see, my numbers is going to be bigger in here. If it's, this one is y value is 2, that is going to be 3, 5, 9 some numbers. I'm just saying as my y value. So one by one, think about here. I had a 2 here. Then the relationship, these two are reciprocal to each other. So flipping top and bottom. So if I had a 2, what do I supposed to have here? 1 over 2, right? If I plug in 1 here, then I get 3. So if I plug in 1, I get 1, 3. That means what will be the value when I plug in 1 here? That's going to be, instead of 3, I'm going to get 1, 1/3 because my function is reciprocal to each other. So I want to see that if you can analyze the graph differences by using your quadratic function. When I look at quadratic function, that's going to be 3, then I get 1/3. And then next one, when I plug in 2, actually I get 7. Then when I take the reciprocal, I have to have 1 over 7. So I can actually get those numbers by comparing those two functions as a reciprocal. So if you continue, whatever my number gonna get bigger as like 100, then my reciprocal function will be 1 over 100. So that's gonna be very close to my x-axis. So my shape of the graph for when you have a positive and rational function do not have restriction for the domain, then your graph is gonna usually look like this shape. So this is the shape of the next function, and this is why this is calculus. So now let's answer. Is this function continuous on interval -1 to 1? Yes. How about 1 to 3? Yes, because it's going to be continuous everywhere. Domain is all real numbers. Then let's try to answer one by one. What's going to be limit when x goes to infinity? That is going to be, as I see, it's going to get close to 0. And then next one, also look at your paper. Oh, that was negative infinity. Sorry, I didn't read that. But still same answer. It goes to 0. And then next one also 0. But are they meet? That's what I'm talking about. Are they ever going to meet? No, it's not going to meet. But the numbers are getting closer to 0. That's what we were talking about the function here, all this is 2. I'm talking about 1.9. The numbers are closer to 2. So although this function never going to meet 0, I know that limit is getting closer to 0. Okay? And then next one, what is the limit at x is going to 0? Do we have a limit? Yes, it's continuous, so it has to have, at that time when we plug in, 1 over 2 as value. Why can we plug in? Because it is continuous. Then how about f of 0? I do have that value, that is 1 over 2. So in this part gives me really, really good review here. There's so many hidden meanings I can see right now. As you see that this is the definition of horizontal asymptote. And then if limit goes to 0, that's, if it goes to infinity, it becomes a definition of a vertical asymptote. However, it doesn't. This one is going to just continuous function and 0, 1 over 2. And when you see these two, also what can you conclude? Your limit is the same as your function. So I can say that at 0, this function is continuous. Then do I have a vertical asymptote? No, but we have a horizontal asymptote, y is equal to 0. But before you answer, I want you to compare these two relationships as a reciprocal. Okay? Class, we're almost there. Now we are on dessert part. As you see that the concept is becoming a little more abstract, so make sure you go over and then repeat the videos if you're confused. Always come to office hours. So today, dessert part, I'm going to see how we can make the function connect to each other and then forcing to make connected function or continuous function, and then I'm going to explain why the intermediate value theorem is. That's today's dessert part, a little bit challenge part of it today. So I have one function is kx squared plus 2x. Next function is 2x plus 4. These are, as you see that these are piecewise function. Then I wanna connect these two functions somehow. So as you see at 2, they are disconnected, but making magic number of k, I can probably connect that here. So how are we gonna connect? I wanna plug in 2. Then at that function, I will get my y value as 4k plus 4. Then if I plug in second part of the 2, as you see there's inequality differences, right? So this was slightly less than 2, this was at 2 and then bigger. So if I plug in at 2, then I'm gonna get 8. So if this function looks like quadratic, something like this, then this function is a linear function coming that, and it can be disconnected. However, I want to connect them from 0 to 5. They are make sure they're continuous. That means I have to have the same y value at 2. So I'm going to set my equation equal to. It's like a solving system of equations. Then 2k plus 4 has to be 8. So k is equal to 1 here. I went really fast, right? That is moving 4 to the other side, that is a 4, so k is equal to 1. So if k is 1, my two graph is going to be connected and it will make continuous function. So now, if you look at those in-class activities, I want you to pause the video and then try to see if you can get the answer quickly. K is equal to -3? Yeah?
I'm still doing it. A little confused.
Oh, you're confused?
I think I'm.
So I'll explain here. So you have a function k sum of the linear function from 0 to 1, right? And there's another function going like this. I don't know what the k value is, but I want them to connect it. Somehow if I want to connect, that means my y value has to be the same when I plug in 1, right?
Yeah, I just got it.
So I plug in 1 here, that gets a k, and then I plug in 1 to here, then that gets me 2k plus 3, and then these two has the same, so k has to be -3. At that time, I get definitely same y values. So today's main highlight of the dessert is going to be intermediate value theorem. This one, when you look at the theorem itself, a little bit confusing. So let me just read it what it means, and then let me show you the example that will give you clear meaning of the intermediate value theorem. So there's a function, it has to be continuous, make sure you circle it, because we only study continuous function in calculus, and then it's going to be closed interval, which means your domain is closed from left to right side, both has a closed circle, that's what closed interval means. Then let n be any number between here. So as you see, this represents your y values, those are y values. So n will be any value between those y values, where those are not the same. So y value is not the same, then there must exist the c value that will go to n value. Okay, so meaning is a little bit weird. So if it's a continuous, my graph is going to starting point and then I'm going to have end point. What they're saying is, let's say that this coordinate is 1, 1. This coordinate is 3, 5. Then it is a continuous closed interval, and between those two A and B as input are not the same, A and B are not the same. So these 1 and B, 3 are not the same. These two numbers not the same. Then your output also not the same. As you see, output is not the same. That means your graph is not like this shape. Come back to same. You cannot. It's going to be different number. Either this number has to be bigger, or either this one has to be smaller. Then there exists a number. So that means that there will be a number between these two no matter what. That means, do I have to have a 2? Yes, because it's a continuous function that I cannot jump from 1 to 3. Like you cannot only have 1 to 3 kids. Like you have to have a second kid to have a third kid. So you cannot just jump it. So I must have number 2 because it's continuous. So the number exists between two numbers. That means there will be also number existing y between that. What does that mean? When do we use this one? I just will give you a clear example. So class, let's look at the example 5. Actually, I changed the question here, so just be careful when you look at from the previous video, it will be slightly different. So let's look at the example. What happens if I have a x cubed minus 2? If I plug in 0, I'm gonna get negative 2. And if I plug in 2, then I'm gonna get a minus 2 as a 6. So I know that this one is a polynomial, it's a continuous function. And what I am saying here is, one of the graph, when I plug in 0, I got negative 2. When I plug in 2, I got 6. So although you see the graph shape, some of you guys, but what I try to say here is, no matter what, I must have 1 0 exist. 0 means the solution, 0 means x-intercept, 0 means root, all the same meaning. So when you look at here, by intermediate value theorem, sometimes we also have a similar one as a intermediate mean value theorem is going to be very similar one as well. So when you see here, when I plug in 0, I got negative number. When I plug in 2, I got positive number. Then I do not know exactly what that number is, but it must exist at least one x-intercept. Why? Because it's continuous that in order to get from negative to positive, you must cross the x-axis. So that shows that you must have a solution here, at least one of them. That's how we use intermediate value theorem. So let's practice with your in-class activities. I want to try again with me one more time. I put those values here. So first of all, I want to plug in 0 for your original function. Then cosine 0 minus 2 times 0. Cosine 0 is 1, so don't forget I get 1 here. And the next one, we are going to plug in next number. Then what we're gonna get here, we can punch into the calculator. I'm gonna punch into the calculator quickly. Cosine 1, I think it should be radian. And minus 2. Then I get negative 1.4596. So although I do not know this graph, but do I have at least one root? Yes, I have to have it. When I plug in 0, I got 1. When I plug in 1, I got negative 1.4. So whatever the graph is going to look like, I have to have 1 0. Sometimes we can find it, sometimes we cannot find it. It's not easy. In this case, it's not easy to find besides using graphs. So at least by using the theorem, you see that there is at least one root exist. It's better than not knowing, right? So that's how we use intermediate value theorem. And I want you to remember intermediate value theorem. I usually indicate as IBT theorem. Okay, so that's it for today. Good job.